Welcome to DP Tutorials by Tony Jarwa. In this teaching module, we will learn on another topic, which is the electric potential due to an electric dipole. We have learned previously that the electric potential due to a point charge is given by the expression, okay, is given by the expression E equals sine 1 by 4 pi epsilon naught q divided by r square, not E. When we talk about potential, the the symbol is V. V equal 1 by 4 pi epsilon naught q divided by r. So over here, when we have a dipole, we have already learned that a dipole is a system of two unequal charges separated by a finite distance between them. If one charge is minus q, the other charge will be plus q. So this will form a system of a dipole. And the length of the dipole, or the dipole length, will be equal to twice a. We have learned about all these discussion. Then in this case, we will consider that let a dipole whose length is twice a, okay, whose length is twice a, which means that O is the center of the dipole. Then one part will be A and another part also will be A. Then over here, the minus charge is located at point A and the plus charge is located at point B. When we have learned about electric potential, we know that for a negative charge, okay, for a negative charge, the electric field will be negative, 4 minus q. And for a positive charge, okay, the electric potential is positive. So the potential for minus charge will be negative and the potential for positive charge will be positive, which means that V for minus charge will be negative and V for plus charge will be 1. It will be positive. So those are the peculiar informations or key ideas that we need to recall. Okay, so over here we have considered this electric dipole, and let this dipole be placed at a certain point. This is your electric dipole consisting of charge minus q and plus q, placed at point E and point B, and the dipole length is twice A. Then over here we consider this point P, okay, this point P, and let that point P, whose distance is OP from the center O, okay, from the center O, this distance be equal to R. So from O up to P, let us denote that this distance is 1. This distance is R. Okay, we will let that distance be R. And from here, that means by the help of these points, okay, by the help of these vectors, we can find, okay, let the distance, okay, let the distance from B up to P, okay, let the distance from B up to P be for R2, okay, let me put this as R2, let the distance be R2, and let the PV from A, or let the distance from A up to point P be 1, be R1. So these are our respective distance. So from here, AP equal to R1 and BP equal to R2. These are our respective distance of the charges. AP of minus Q, BP of plus Q. Then we have to write down the electric potential of the minus charge. I have explained that the electric potential due to the minus charge is negative. So from here, we will use this formula. That means it will be minus 1 divided by 4 pi epsilon naught, then Q divided by 1. Q divided, what's the distance of minus Q? Of minus Q, the distance will be R1. So negative sign. For a negative charge, the electric potential V1 is always negative. So this sign will take care of that. Then similarly, the electric potential due to this plus Q charge. So over here, that means we have to write it is positive. So we will write 1 by 4 pi epsilon naught 1 by 4 pi epsilon naught q divided, what is the distance of that BP? The distance of BP will be equal to 1. The distance of BP will be equal to R2. So we will write R2. Yes, so we will write R2. And over here, since it is positive, we need not write positive. Why positive? Since it is for what? For a positive charge. Okay, so this will be 1. V2 will be given by that expression. Need not write the positive sign. Then, why we are able to write these expressions of electric potential V1 and V2 in this form? Because we are using this concept. This is the electric potential due to 1. This is the electric potential due to what? Due to a point charge. Due to a point charge. Due to a point charge. Then, from here, in order to find the resultant potential, our strategy is to find out what is the potential at this point P. So in order to find the potential at point P due to minus Q and due to plus Q, you have to add these V1 and you have to add V2. So that will help us to find what? The resultant potential. So the resultant potential will be obtained by adding V1 and V2. So from here, V1, what is V1? V1 will be minus 1 by 4 pi, okay, minus 1 by 4 pi epsilon naught Q divided by R1. Then we have plus, for V2 it is positive, then we will put 1 by 4 pi epsilon naught, then we'll have Q divided by R2. So we can rearrange this equation. Okay, we can rearrange this equation in the sense that we will take, okay, Q outside and that 4 pi epsilon naught also outside. Then we are left with some terms. Over here you have minus 1 divided by r square. So I will write this will be minus 1 divided by r square, and we have what? 1 plus 1 divided minus 1 divided by r1 plus 1 divided by r2. But over here, in order to be more presentable, we will write R2 first and we will write R1 after. So over here, we will write in this way. R2 minus R1. 1 by R2 minus 1 by R1. So this is the expression for V. Okay, the expression for the electric potential at P. Electric potential at P will be given by 1 by 4 pi epsilon naught. Okay, 1 by 4 pi epsilon naught Q. From here, that means this will be equal to 1. This will be equal to 1 divided by R2 minus 1 divided by R1. So our target here is to find out the values of R1 and R2. We don't know what are these values of R1 and R2. R1 and R2 are unknown. Okay, R1 and R2 are unknown. So you have to determine what is these values of R1 and R2. So some geometry is needed. So in order to find these values of R1 and R2, we have to draw some geometrical constructions. Okay, we have to draw some geometrical constructions. So in this case, let us draw some lines. Okay, we will draw some lines from E up to P. Will drop a line which is perpendicular, and from B up to this OP also will drop some line which is perpendicular. And from here, we will find out what is the relationship of this R1 and R2 in terms of small r, which is the distance of the point P from the center O of the dipole. Okay? So from here, making use of this vectoral representation, we'll take this vector and I will place, we'll take this vector and I'll place over here. I'll take another dotted line and then I'll place it over here. So let us draw, okay, let us draw EQ which is perpendicular on OP produce, and then we will draw this BR. Okay, I will name this as R. Let us BR which is perpendicular on OP. So these are the constructions. These are our constructions. So we will draw Okay, so we will first of all, in order to find R1 and R2, we will draw that okay, we will draw that EQ. We will draw EQ on OP produce. We will draw EQ on OP produce, and that BR and that BR on OQ, on OP, I mean. These are perpendicular. Mind you that under the condition there is EQ is perpendicular to OP produce. EQ is perpendicular to OP produce. That is verified from the figure. This EQ is perpendicular to this OP produce, and BR is perpendicular to not OP produce, EQ perpendicular to OP produce, BR perpendicular to OP. Okay, BR perpendicular to OP. Then over here we will write BR perpendicular to OP. So these are the important cases. Then from here we will consider on some of the triangles. Okay, we'll consider in some of the triangles. Suppose let us find, we want to find R2, so we will consider in this triangle BOQ. In this triangle BOQ, it is evident that this angle is a 90 degree, and let us make an assumption that these angles meet the angle between the equatorial line OP with the center O of the dipole makes an angle of theta. If this is theta, that means this is also theta. So from this triangle, it is clear that this, when you look at OB is equal to how much? OB is equal to A. And we want to find this OR. So how will we do that? Okay, how will we do that? So let us draw some constructions. So we will consider in that triangle. Okay, we will consider on that triangle BOR. Okay, in that triangle BOR. So on that triangle BOR, okay, the triangle. This is the point B where that lost charge is located, and over here, okay, this is the point O. From O up to B, distance is A, and over here we draw this Q, and this is the line. That is the line OQ, and this is perpendicular. So it is obvious that if this is 90 degree, that means this point A is our 1. That point A is our hypotenuse. We are interested in finding this length OQ. So how will we do that? How will you find OQ? By using some trigonometric functions. So cos of what is the angle? This is the angle. Remember that this is the angle. So if this is the angle, that means the side opposite to that angle of inclination, this will be what? This will be our perpendicular. So cos of theta will be base upon hypotenuse. What is this question mark? This question mark is our base angle. Okay, that length OQ is our base angle. So from here, from that triangle, cos of theta will be base upon hypotenuse. Base upon hypotenuse. So OQ upon OB. So over here we have OQ. And what is OB? OB is equal to A. So from here, what do we get? In order to find this OQ, which is unknown, so OQ will be equal to cos multiply A this side, so we'll get A cos of theta. A cos of theta. So next we will find BP. What is that length BP? Okay, what is that length BP? When you look from this figure, this BP will be equal to R. Okay, that BP will be equal to R. So we'll write over here. What is BP? This BP will be equal to R. This BP will be equal to not only R, but it is R2. But this BP, if we have drawn if we consider that the electric dipole is very short, that means this BP will be equal to 1. That BP will be equal to this BP will be equal to PR. Okay? When this is very very small, when we assume that dipole is very very small, that means this length BP, this is your BP, this is your BP, we have, this is the point O, and if you draw this very very small, that means very very close, that means that distance BP equal to R, it is very very equivalent to 1. It is equivalent to this side, BP is equivalent to this side, PR, which means this side and this side, BP and PR are equal. Provided if this point R is very very close to, provided if this point R is very very close to the center O of the dipole. So from there we will write, okay, so from there we will write under that condition BP equal to R2, but for small dipole this will be equal to how much? This will be equal to PR. Okay, this will be equal to PR. But what is PR? Yeah, what is PR? These steps are very very crucial. I will mark this with BP equal to R, but for a small dipole that R is equal to PR I have shown. Okay, then what is this PR? When you look from the figure, okay, when you look from the figure, that PR, this PR, when you look from the figure, that PR, okay, when you look from the figure, that PR is given by this line. Okay, it is given by that line. This is P, equatorial point, and we have over here R, and we have over here O. What is this full distance from O up to P? From O up to P, distance is R. It is given by this. Then you want to find what is PR. What is this OR? Okay, what is this value of OR? We have determined OR from the step below. Okay, OR. What is OR? OR or OQ or 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 OQ will be how much? Will be A cos of theta. Oh, okay. I will write here OR. Okay, not OQ. This is OR. BOR. Yes. Okay, not OQ. This will be R. OR. Over here also. Sorry for the inconvenience. This also will be OR, and this also will be OR, and from here also this will be equal to OR. But what is this OR? OR is A cos of theta. Again, let me repeat. From O up to P, it is equal to small r. Then we want to find what is this PR. What is this PR? What is this PR? PR is question mark. How much is from O up to R? From O up to R, it is A cos of theta. This distance is what? A cos of theta. That distance is A cos of theta. So we can find. So what is this BP? What is this PR? PR, okay, that PR will be equal to 1. Will be equal to OP minus 1 minus OR. PR will be equal to OP minus OR. PR will be equal to OP minus OR. So we will write that expression. Okay, we will write that expression over here. So what is PR? PR will be equal to OP minus OR. So what is OP? OP is equal to that R2. Okay. OP, what is OP? No, not R2. OP is equal to R. OP equal to R. Okay, that OP is that length R. That OP is equal to R over here. That OP is equal to R. So R minus small r minus what is O capital R? O capital R is A cos of theta. So this is our BP, which is nothing but RP. So we will mark this. As equation 1, and then we'll mark this as equation 2. We have determined. Okay, we have determined what is this R2. Next, we will determine what is this R1. Okay, so in triangle ERO, okay, in triangle EQR, I mean, in this triangle EQO, we will consider on this EQO to find out what is the next. Okay, so from here, from this triangle, it is evident that this EQ is drawn perpendicular on this line, so this angle will be 90 degrees. So this is theta is the angle, so this implies that the side opposite to this OA is our hypotenuse. So if we draw, okay, if we draw below on this triangle EQR, okay, on this triangle EQO or EOQ, in triangle EOQ, okay, in that triangle EOQ, how does that triangle looks like? So we have this is the point A where that minor charge is located. This is the center O of the dipole. Then the distance will be A, and then from here we have that line, and then we keep on drawing, and then we drop this line perpendicular. Okay? We drop this line perpendicular. This EQ is perpendicular to that OP produce. Okay, and this angle over here, this angle is theta. So it is obvious that if this is 90 degree, it is obvious that if that is 90 degree, so this side OE will be our hypotenuse. Then this line OQ will be our base, and this line will be our what? Will be our perpendicular. This line will be our perpendicular. Okay. So over here we are interested in finding. What is this OQ. Okay, what is that OQ? So similarly, using the same analogy, over here we will find cos of theta. So cos of theta from this figure, it is OQ. Okay, cos is base divided by hypotenuse. What is hypotenuse? Hypotenuse is OE. Then we want to find OQ, and what is OE? OE value is how much? OE value is small a. So from here we can write OQ, cos multiply this a this side, then you'll get A1 cos of theta. Okay, A cos of theta. So it is similar, it is the same like this expression. So both these expressions are the same. OQ is A cos of theta, and over here OQ it is also one. OQ it is also A cos of theta. Then we will find what is AP. So when you look from the figure, what is AP? From the figure, AP it is equal to R1. Okay, from here we have written that AP is equal to 1, AP is equal to R1, BP is equal to R2, so AP is equal to R1. So when you draw this perpendicular, and when this line is very close, okay, when that line is very close, it is obvious, okay, that this, let me retrace the figure here. So this is our point P, and this is our point A, and this is suppose that point. Okay, that point, this is the point O, and this is our A. When we draw this Q, when this Q is very close to point O, that means this OP, this line OP is also similar to that line OP will also be the same as the line 1, as the line OQ, under the condition that point Q, this point Q is very close to point O. So from here, for small dipole, that AP, what is AP equal to? AP is equal to R1. Okay, AP is equal to R1. So from here, that EP equal to R1, and this R1 is approximately equal to that 1 to that PQ, okay, to that PQ. But when you look from the figure, okay, when you look from the figure, that PQ, okay, that PQ, again, when you look from the figure, okay, that PQ is how much? Again, let me retrace over here. Okay, let me retrace over here. This is point P, this is point O, and this is point Q. Okay, from O up to P, it is equal to R, and this OQ, how much is OQ? OQ is A cos of theta. This is the point E, this is that charge minus Q. From here we have from E up to O, that distance is A, and from here also we have that line, and we drop the perpendicular from here. That means this is that point. Okay, understand? So what is PQ? This PQ, this distance of PQ from this figure, it is clear that it is OP plus 1 OQ. So from here we have to write OP plus OQ. So what is this OP? OP is equal to R. What is this OQ? OQ from this expression, it is 1. It is A cos of theta. So we have determined the values of the values of R1 and R2. So this is the value of R1, and this is the value of 1. This is the value of R2. So I will mark this as equation number 1, or as equation number 3, I mean. So values of R1 is this, and values of R2 is this. So putting these equation 2 and equation 3 on equation, values of R1 and values of R2 has been determined. We'll use this and put on equation 1 to find out what is the potential V due to the dipole. Okay, due to the dipole. So using these values R1 and R2 on equation 1, okay, on equation 1, therefore the potential V is given by Q divided by 4 pi epsilon naught. We have first the value of 1 by R2. So what is R2? Over here we have 1 divided by R minus A cos of theta. That is values of R2. Then we have 1 divided by R1. Then what is R1? R plus A cos of theta. Okay. So we will solve this expression. We'll try to solve this expression, and then we'll find out what is the result. Then over here, this will be Q divided by 4 pi epsilon naught. Then over here we have to find out the LCM. The LCM will be R minus A cos of theta, and over here you have to write R plus A cos of theta. When you divide this to this LCM, that means you'll get R plus A cos negative sign equal to negative. When you divide this denominator to this, you'll get what? R minus A cos of theta. Put that within bracket, and then we use this big bracket. Then from here, this quite obvious that this will be Q divided by 4 pi epsilon naught. Then the terms inside the numerator is like a square formula. We have R minus A, R plus A, so we'll have R square minus A square, okay, cos square theta. And then if you remove the bracket, okay, if I remove the bracket, some of the terms will get cancelled from the numerator term. Okay, from the numerator term. So minus into plus will give you minus, minus into minus will give you plus. So over here will give you like that. So some of the terms from here will get neutralized like this term, and this term will get cancelled. Okay. So what are the surviving terms? Only this and this will survive. Then we will have the final expression, okay, the final expression of q divided by 4 pi epsilon naught. Okay, over here you'll have a cos of theta, but since there's a plus, you'll have twice a cos of theta, and over here you have that denominator term r square minus e square cos square theta. But when you remember, okay, when you remember that expression, that P, that electric dipole moment P, it is equal to Q dot twice A. What is this? This is our definition or the concept of electric, okay, dipole, electric dipole moment. Electric dipole moment. So this term Q and twice A, it is nothing but your one. It is nothing but P. P is what? P is our electric dipole moment. So P is Q dot twice A. Electric dipole moment. So from here we can write this final reduced expression as 1 by 4 pi epsilon naught. Then in place of this we'll write P, okay, cos of theta, where P is Q dot twice A. Then from here we'll have that expression of r square minus a square 1 cos square theta. This is the general expression. Okay? This is the general expression for the electric field of an electric dipole at any point. Of an electric dipole at any point. The general expression for the electric potential due to a dipole at any point. So from here, this is that expression. This is that expression. Then we will put an assumption in which we consider for a small dipole. Then for a small dipole, we will have a condition that R is very large than A. Okay? R is very large than A. That means over here, if I draw a dipole of this form, that means this is minus Q and this is plus Q. Okay, that is minus Q, that is plus Q. And from here, this is the point P, and this is that distance. This is point R, and this is A, and this is A. That means for dipole, these two points, these two charges are very close. Point A and point B are very close to one another. In this case, for a small dipole, it means that one. What does it physically mean? That means R is very large in comparison to A for a small dipole. So when R is very large in comparison to A, so when you take A square term, even if you take the square of this number, this will be even smaller. It will be even smaller. So that is why this term A square cos square theta is small and it can be omitted or it can be neglected. So that term A square cos square of theta can be neglected. Okay? So when you neglect that, under the condition that the dipole is very small, so the total potential, the total electric potential will be given by this formula: V equal 1 by 4 pi epsilon naught, okay, P cos of theta divided by 1, divided by r square, okay, divided by r square. So this is the resultant, okay, resultant formula. This will be the resultant formula for the electric potential, for the electric potential Due to what? Due to an electric dipole. And when you look from this expression, it is very, very clear. Okay, it is very, very clear that that potential varies inversely as the square of the distance. Varies inversely as the square of the distance. And if you remember from electric field due to a dipole, the electric field due to a dipole, it is given by this expression 1 by 4 pi epsilon naught, okay, for point on the actual line or point on the equatorial line, it is given by this expression, okay, it is given by this expression, and this is E axial, and then E equatorial is given by 1 by 4 pi epsilon naught. Then you have that expression P, this is x cubed, okay? This is x cubed, and then you have P divided by x cubed. From these both these results, E, okay, it is inversely proportional to the distance or the cube of the distance, But in case of potential, the electric potential varies inversely as well as the square. In case of electric field, it varies as well. It varies as the cube. In case of potential, it varies as well as the square. So those are some of the terms that we need to consider. So from here, we'll study some special case. Okay, we'll study from special case from this resultant formula. So from here, let us assume that this point P, is on the axial line. When I say axial line, that means this is our axial line. Okay? That is our axial line. When this point P is located over here, or when this point P is located over here, point P, it might be here. That means this is point on the axial. This point over here, that means this will be one point on the equatorial line. Those are the special cases. So from here, point on the axial line. So for point on the axial line, if we draw the figure will be in this case. Okay? So we have, this is minus q, this is plus q, okay? This is the center O of the dipole, and if I take a point, suppose a point P, which is on the axial line, then from here, the electric dipole moment, always remember, it is measured from minus charge to plus charge. So this is our electric dipole moment vector. And this distance from O up to P, what is that distance from O up to P? That distance from O up to P is that distance R. So it is very, very clear that if you draw only the vectors, if you choose only the vector, that means the P vector is acting on this direction, and this R vector is acting on this direction, which means that both P vector as well as your R vector are acting in the same direction, which means that in this case, the angle theta will be equal to 0 degree. Okay? The angle theta will be equal to 0 degree. So that is why when you put on that equation, that means what do we get? We have 1 by 4 pi epsilon naught. I will write this as VA or V axial. Then over here we have P. Then in case of 0 degree, in case of theta, I'll put as 0 degree, and over here we have R square. Cos of 0, how much is cos of 0? Cos of 0 is equal to 1. Okay? Cos of 0 is equal to 1. Then over here we have 1 by 4 pi epsilon naught. Then over here we have V into 1 divided by R square. This is our VA. Then, which means that our V axial, okay, potential along the axial point is given by 1 by 4 pi, okay, 1 by 4 pi epsilon naught P divided by R square, which is the case in which the potential, that means electric potential of an electric dipole is maximum for the case when the point is located on the actual line. Okay? On the actual line, the electric potential due to a dipole is maximum. Now let us consider the case when the equatorial, special case number 2, when the point is on the equatorial line. Now again, yeah, this is the point. See, this point P is on the actual line. Now let us put an assumption in which the point P is located on the equatorial line. So this is our dipole. This is minus Q. Okay? This is minus Q. This is plus Q. This is the center O of the dipole. Okay, and then if I draw this line, okay, and this point P is located along one. This point P is on the equatorial line. This point P is on the actual line. Okay, actual line. Then from here, see, when you look vectorially, what is the direction of the electric dipole moment vector? The direction of the electric dipole moment vector is always taken from the minus charge to the minus charge to the plus charge, always on the minus charge to the plus charge. So this is our electric dipole moment vector. Where is the direction of OP? The direction of OP is in this direction. It is obvious that from this figure, P vector is in this direction, which is this, from minus Q to plus Q, and R vector is perpendicular. This R vector, okay, that R vector is perpendicular. Okay, this R vector is perpendicular, so that is the R vector. This is our R vector. It is obvious that this angle over here is how much? That angle over there is 90 degree. This angle is 90 degree. So for a point on the equatorial line, the angle between P and R is how much? It is 90 degree. So when you put on that equation, this equation over here, when you put on this equation, then this will be equation number 4, I guess. Okay? When you put on this equation 4, that means in place of theta, you'll put by how much? 90 degrees. So when you put over there, you'll get the value to be equal to 0, because cos of 90 degree itself is what? 0. For actual point, theta we put as how much? 0 degree. But for the equatorial point, theta will be how much? 90 degrees. So put over here 90 degree divided by 1, divided by r squared. So when you solve, you'll find out that this expression reduces to 0 under the condition that cos value of 90 degree will be equal to 0. So this term itself, Vp, or I can write V equatorial, this V equatorial is equal to 0, which physically means that the electric potential of a dipole on the equatorial line is 0. Or we can speak of it as a case in which the potential is minimum. Okay, the potential is minimum when the point is on the equatorial line, and the potential is maximum when the point is on the actual line. When the point is on the actual line, the potential due to the dipole is maximum. When the point is on the equatorial line, potential due to the dipole is minimum. And from here, the plot. Okay, so you have learned from here that see, this potential varies as the square. So when you plot a graph, now we will study the plot of the potential versus distance. So when you plot, along the y-axis we'll choose the potential, and along the x-axis we'll choose the distance. When you plot, you'll get these types of graph. Why? Because V is given by this expression 1 by 4 pi epsilon naught, okay? P, okay? P cos of theta divided by 1 divided by r squared. P cos of theta divided by r squared, or simply we can write V is inversely proportional to r square. That means as distance increases, as distance increases, your potential V will one. It will decrease. It will decrease. It decreases with distance. So it varies as the function. Okay? Your potential or electric potential, it one. It varies. It varies as the inverse of square of distance. Square of distance. Square of one. Square of distance. So this derivation is important from examination point of view. We just review through the rest of the discussion so that you will understand the key features pertaining to this interaction. Until we meet again, thank you.